Okay. So maybe we can start. Okay, yeah. So good afternoon, and so let's continue. So today we will see some more rules, and possibly the last set of rules. Okay, let's see. So as I mentioned last time during the summary, we had not seen rules for negation. Okay, so how to deal with negation operator? So yet again, there are two rules: introduction and elimination. So how do we introduce a negation? If I want to derive something of the form not phi, how do I do that? I will assume phi, and if I'm able to derive bottom, okay, then it means that this is a contradiction, okay, and then I can derive not phi, okay. But then how can I derive a bottom? So this is called the bottom introduction or the negation elimination rule. If at some point of time I have derived both phi and not phi, then I can derive a contradiction, which is a but. Okay, so we will see examples. But so here are the two rules. If I want to derive not phi, I will first start with phi and keep doing my rules. And if at some point of time I derive a bot, then it means that this assumption was wrong. So I can derive not phi. But then when can you derive a contradiction? If you are able to derive some formula phi and not phi within the same context, then it's a contradiction. Okay, so let me copy this. And so here is an example. So please try it out. I will just keep these rules so that you can. So yeah, take your time. I'll discuss after a while. So maybe I will do this, and then just to give an idea of how it goes. So as usual, I write P implies Q to be a premise. P implies not Q to also be a premise. See, I want to derive not P. Okay. So somehow I should assume P and arrive at a contradiction. And then I can get not P. Right? Now, how do I introduce bot? I should be able to derive a formula as well as its negation. So first, let me assume P. Okay. Now, using this premise and this assumption, and using the, what is that, implies elimination rule, what do we get? We can get Q by applying the implies elimination on 1 and 3. Okay. Now, using this and the implies elimination, you get not Q. Now you see that I have derived Q as well as not Q. So this is a contradiction. So I will introduce bottom. Thanks to, I'm using the, so I can either call this the bot introduction or the negation elimination. It's fine, whatever you write. Okay. So negation elimination rule on, actually calling it the bot introduction rule is much more, okay. Bot introduction on 4 and 5. Okay. So this, I can close my assumption. So starting from P, I have derived bot. And then I can use this rule. Oops, I can use this rule to derive not P. Using the rule negation introduction to the lines 3 to 6. Okay. Yeah, so we have used implies elimination, the bot introduction rule, as well as the negation introduction rule to derive not P. So please type yes if you have understood this. Okay, good. Okay, so yeah, so just a remark. So formulas of the form phi and not phi are called contradictions. Okay, and so this phi can be some P, or it could even be P implies Q. So this is P implies Q and not of P implies Q. Okay, so any phi and not phi is called a contradiction, and this rule is proof by contradiction. So in general, when you write an English text of a proof by contradiction, what do you do? Assume something, you get to a contradiction, and then you derive. So then you say that hence our assumption is not true. This is exactly that. Okay, it's just that it's pinpointing things, and it's a very methodical application of proof rules to get a contradiction, and hence you derive the negation of it. Okay, that's all. So this rule is called proof by contradiction. So try this example. You can, so this can also be used as a rule sometimes. It's called a Mulder-Stollens rule. Anyway, but just try to derive this sequence. By the way, if you are done, just let me know. So if a sizable number of you are done, I will give the answer. Yeah. Okay, so it's time to give the answer. Okay, so I will start with phi implies psi is premise, not psi is a premise. I want to derive not phi, so I will assume phi, and then I will use the implies elimination to derive psi on 1 and 3. And then I have derived a contradiction using 2 and 4. That's it. So I derive not phi from the negation introduction rule applied to 3 to 5. Okay, so good. So let's carry on. I think try this out. Okay, so so before you scratch your heads even further, I think it's not possible to do this with the given set of rules. We have to introduce another rule to get this. Okay, but just out of curiosity, did you manage to get an answer for this with the, yeah, I think, okay, good. So no is good. Okay, so see, so how would you proceed? So I want to derive P implies Q. So how do you usually derive P implies Q? You want to assume P, do something, 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 and then in the end derive Q, and then you want to introduce P implies Q. This is what you want. Okay, so the second thing that you will do is, what is the premise that you have? You have not P or Q. So somehow you want to eliminate this not P or Q. So what will you do? So if I'm able to derive not P, sorry, if I'm okay, starting from not P, if I'm able to derive Q, and starting from Q, of course I have derived Q, then by using the OR elimination, not P or Q, so from not P I derived Q, from Q I derived Q, so the chi is Q. Then you can eliminate this OR and write Q. This is fine, except that we still don't have this. Okay, this part is the mystery, right? So if I have not P, let us zoom this. I have assumed P. So I have arrived at a contradiction. Okay. But I want Q. Okay. So here is where we will introduce a rule which says that whenever you have a bottom, you can derive any formula out of it. Okay. So there is a rule for, okay. So this confuses with, okay, I see. Yeah, no, this is the bot introduction. Okay. So now we have two rules for bottom. One is the introduction rule, which is the one which we have already seen. We are going to have an elimination rule. So if I have a bot, I can derive any formula. Okay. Why is this? The intuition is that bot implies phi is always true. Because whenever, I mean, if you look at the truth table of P implies Q, when P is false, this implication is always true. So instead of P, if I use the symbol 0, which is exactly bot, this means that this implication is always true. Bot implies any formula is true. So if at some point of time you have derived a bottom, then you can derive anything. Okay. So now if we redo this question, I will redo it properly. And I also put this okay, let me redo this. Not P or Q is the premise. Okay. Now I want to derive P implies Q, so I will assume P. Okay. And then my premise is an OR. So somehow I need to apply OR elimination. So then I will make an assumption not P. And then I will derive bot due to 2, 3. And then once I've derived bot, I will conveniently derive Q. Okay. By applying the bot elimination. So let's call this the bot elimination. Bot elimination applied to 4. Okay, fine. The second thing, starting from Q, if it's an assumption, I can just derive Q. I just say copy 6. Now you apply the OR elimination to not P or Q, this part, to get Q by applying the OR elimination on the premise, this 3 to 5, 6 to 7. And so inside this context, you have derived Q, which means P implies Q. This is the implies introduction applied on 2 to 8. Okay, so there's a question. Is there a problem if we take OR boxes? No, it should be fine. So you're saying that, okay. So wait. So your alternate method is that you have not P or Q. So you will first start with not P. No. So how do you derive P implies Q? Wait. So, okay. So then inside you have to derive P implies Q. So the question is there a problem if we take OR boxes to be the outer boxes and assume P inside both? So then you should be able to derive, then you should try to derive P implies Q on both. Yeah, this is also possible because, so here you will derive what? P bottom. So then you can derive, wait, let's try this out properly. So I will create a new. So first of all, I hope this part is clear. So here's an attempt at a different way to do it, which is, so let me say that not P or Q. is a premise. I want to eliminate this, so I will assume not P first. And within that, I assume P, I get a bot. Okay, so then I can derive Q, say. So here I derive P implies Q. Okay, then I assume Q, and once again I assume P. Yeah, and just copy Q, and then I can derive P implies Q. Yes, fine. So you can do that. And then you do OR elimination to get P implies Q. Yeah. So this is also fine. Does that, yeah.
But it's almost the same, right? We are anyway using bot
Yes, yes, yes.
inside. So
Bot,
instead
bot,
of P and
yeah.
not P, we are doing not P and P in that order,
No,
reverse
no.
order,
So
something like
here
that.
we started, yeah, here we assumed P. Yeah. So that's what. So here, we interchange the rules in some sense. So here we had the implies
Yeah.
introduction, and inside that we did an OR elimination. Here you are doing an OR elimination, and inside that you are doing an implies introduction. So, yeah. But we had to use the bot elimination in both the cases. Second box isn't clear. Wait, wait. So this is why, wait, wait. Let me just, this is 3, 4, 5, 6, 7. See, I assumed Q. And inside that box, I am first assuming P. Okay. So I want to derive P implies Q inside this box. But then if I have assumed Q, I can take any assumption here, 8, and I can just copy the assumption inside this. Okay, because inside that context, Q is true. So it doesn't really matter. It could have been anything here. Okay. And so inside, see, this is to apply the implies introduction, because for the implies introduction, I need a box which starts with P and ends with Q. So I got it. And then I got P implies Q. Okay. So I have both of them, and now I do OR elimination on this, and this. So the point of this problem is to say that if I have a bot, I can derive any formula. So is this thing clear? Either this method or this? One of them is clear. Can you just say yes, please?
Yes, sir.
Okay. Yeah, very few cases.
Sir,
Yeah.
sir, if it was
Hmm.
not P and Q,
Huh.
then if somehow we derived bot, then uh, could we write that? Write Q in that fifth position?
No, no, no. Wait, what is your question? If I have a bot, I can always write Q, no matter how I got that bot.
Okay, no, just I am not proving this premise. Fine, proving this sequent. I am just saying that not P
Huh.
and Q is there.
So then you already have Q. You don't have to go through bot. Wait, wait, wait.
Okay.
Let's see an example.
Sir, assume P means we are assuming P to be true.
Yes. See,
Okay.
you remember the implies introduction rule?
Yes, sir.
How do you, if I want to derive phi implies psi, I will assume phi. Assuming that phi is true, I am able to derive psi by repeatedly applying these rules.
Okay.
Just apply the rule. Okay, so in order to get phi implies psi, I need to have assumed phi, and inside that box, I need to have arrived at psi.
Okay, sir.
Okay, yeah.
Actually, sir, here if we just logically, not formally,
Okay,
if P is true, then not P is always false.
right?
So when not P is false, then Q should be true to make this not P or Q statement to be true.
Come again. So it will just be a rewording of this proof. So tell, if P is true,
Hmm.
then what are you saying? Not P is always false, right? That is what is meant by assuming, by getting bought here. And
So
then
for this premise to be true, then Q should be true.
which premise to be true for this?
Number one.
Okay. So you're saying if you're saying so you have not P or Q and you have no. So sorry. What is your come again? Sorry.
Sir, I am just talking in the terms of truth tables. If we assume P1, then not P is 0.
No. See,
Means,
yeah, I think we should not mix the truth table business here.
Sir,
Okay.
sir, she's
Uh,
talking in set theoretic terms. So not P or Q is true, then at least one of them must be true. And if we know that P is not true, then Q must be true.
Yeah.
Something
See,
like that.
this you can see. I mean, in fact, the truth table of P implies Q and not P or Q is the same. Okay. So if this is true, this is true. That from the truth table, it is clear. Okay. But we want to derive it without making use of this semantics. Yeah. Starting from this, can we syntactically apply the rules and get to this? That is the point. So no. So surely you should not do the truth table analysis here. This is a different kind of a reasoning. Where the goal is to just apply this pattern matching rules to derive the conclusion. Is this of course we have to be consistent with the truth table. I mean, we cannot derive random things. Okay, so it will be like it will be consistent with the truth table, but it is derived by a mechanical application of the rules. This is a different way of doing the same thing. I mean, here it was simple, it was easy for you to look at the truth table, but you have like some 100 premises and one conclusion. It's not obvious immediately. Okay, but of course we cannot do that on by hand. That's why we are doing these kind of things. Okay.
okay, sir. Okay,
Yeah?
sir. I understood. Yeah.
Okay, so the negation part is done and the bought part is done. So there's one more rule, which is the double negation. So if I have not of not phi, you can rewrite it as phi. Okay, it's called a double negation elimination. So there is no introduction for this. So you don't want to introduce a double negation. You just want to eliminate a double negation. Okay, so this looks, I mean, natural. Now, well, I will do this. I am not even going to ask. So phi is premise. Okay, actually I will ask. So how do we do this? So just try this out. So I'll give a couple of minutes. So
So can you please show the previous slide once again?
I will copy this. I'll copy the previous slide. So this is the double negation rule. So I have a premise phi. I want to derive not phi. Okay. Yeah, so let me try it out. So I have phi is a premise. So I want to derive not of not phi. So somehow if I start with not phi, if I get a contradiction, then I can derive not of not phi. Okay, so actually this rule is not even needed. So I will assume not phi. Okay, and then what happens? I will get a bot because of bot introduction to 1 and 2. So I do not of not phi. This is the negation introduction. Sorry, negation introduction done to 2 to 3. That's all. So sorry about
Sir,
putting this thing here. Yeah.
sir, will this not of not phi will not come in the assume box itself only? Like,
Sorry, come again. Ah, no. So no, it's outside the assume box because starting from not phi, if I assume that I get a contradiction, so I know that not of not phi is true. I mean, you can put it here, but in fact, this is the strongest statement to put it outside.
okay.
So you remember, okay, let me put the corresponding rule. This is not the correct rule.
Even the rule, it is outside.
In the rule, it is outside. Yes. So where is the rule? The negation introduction rule. See, if you see this, starting from phi, if I derive a bot, I close this assumption and then I just derive not phi. Okay.
Yes, sir. I wrote it wrongly actually. The rule.
Okay.
That's why.
So let me just copy this so that. Yeah. So now let's go to the next example. Try this out. Okay, so let me give you the answer. So first I write P as the premise, not of Q and R. So second premise. See, I want to derive not P and I have to derive R. And then I can use the AND introduction. So first, how do I derive not P? So first I can assume not P and I get a bot. This is like the previous question. Okay, you get a bot because of 1 and 3. And so then now use an negation introduction for 3 to 4. Okay, you get not. Next, I want to get R. So I will use the double negation elimination to get Q and R first. Double negation elimination on 2. And then I just use the AND elimination on 6 to get R. So now that I have derived not P and I have derived R, I can introduce the AND to 5 and 8. Okay. So is this fine?
Sir,
Yes.
if we just do that not Q or our elimination in the third step, will it be okay, or we have to assume that not P first?
No. You can reorder this. I mean, that's okay.
We can
That's not a
reorder,
problem.
na?
Yes.
Okay, sir. Okay.
That's not a problem. Okay, guys. So just type yes if you have understood this. I just want to know how many are. Okay, good. So now time to go to the next step. Try this out. So there'll be some more examples. Yeah, so try this out. Okay, so here it is. So you have not phi implies bot is the premise. Now I want to derive phi. Okay. So from not phi, I make an assumption and I use this implies elimination on 1 comma 2 to derive bot, and what do I get? I get not 5. Okay, the negation introduction done to 2 to 3, and then I use the double negation elimination on 4. Okay, yeah, so this is the story.
Excuse me, sir.
Yes, yeah.
Sir, bot derives anything. So in step 4, can we directly write phi instead of not phi?
So bot derives anything inside this context.
Okay.
Here you can write anything, but I want to write it outside. You understand?
Yeah, yes.
Good. Okay. What is this? Yeah, try this out. Let's see. So I'll give some, say, 4 or 5 minutes. Yeah. Let's try to take a look. Okay. So the idea is I have to derive not P and I have to derive not Q. So in order to derive not P, somehow I have to assume P and get a bot. And I have to assume Q and get a bot. Okay. So this is the idea. So not of P or Q is my premise. First, let me assume P. Okay. Now, if you remember the OR introduction, if I have P, I can just introduce P or Q by the OR introduction done on 2. Okay. Now this gives me a bottom from the premise, bottom introduction on 1 and 3. So then I can write not P. Okay, by the negation introduction done to 2 to 4. Now I have to do the same thing. I assume Q. And then what happens? I can introduce P or Q by the OR elimination done on 6. And then I get a bottom due to bottom introduction on 1 and 7. Okay. And hence I have assumed, so I derived not Q. Okay, by the negation introduction done from 6 to 8. Finally, I get not P and not Q by the AND introduction done on 5 and 9. Okay. Yeah. So I'll let you look at this. Now I'm going to the next thing because this will take some time. So the previous thing, please do, if you have not understood it, you just take a look at it later. Try to derive this. So there is no premise. Okay. Without any premises, we can conclude phi or not phi. Either phi is true or not phi is true. So, but we have to be able to derive this without any premises. So try this out for some 5 minutes and then I will give you the answer. So let me give you a hint. The previous example would be useful. What was the previous example? This could be useful. The proof of this. Yeah. So let's try to do it. Yeah. Okay. So the main crux here is to start with the right assumption, which is I will try to assume the negation of what I want to derive and then arrive at a contradiction. So I will assume not of phi or not phi. Okay, this is my assumption. So I start opening my box here. And then using the ideas of the previous example, see here, instead of P, I have phi. Instead of Q, I have not phi. And just apply the previous example and you should be able to get not P, which is not phi, and not Q, which is not of not phi. And use the negation elimination to get phi. So let me do it. So using the previous example, you should be able to derive not phi and not phi. Using, I'm just writing using, but using ideas similar to previous example. Okay. Now, from here, you derive not. From here, you have derived not phi using the and elimination on 2, and you also derive not phi using the and elimination on 2, and hence it gives you phi, which is the double negation elimination on 4. Okay, so now what? So now I want to derive, in fact, I don't even need this. So let me even remove this. So I have derived not phi, and then immediately I can derive phi or not phi using the, sorry, I have to derive bottom. Okay, sorry. Okay, I did this. Then I also had not phi, which is coming from and elimination on 2, which is just, okay, and this is enough to show but. Okay, because I have derived a phi and a not of that. Okay, and then I get a bot introduction on 3 and 4, and this will give me phi or not phi by doing a negation. I have to do, in principle, I'll get a not of this negation introduction from 1 to 5, and then I can do a negation elimination to get phi or not phi, a double negation elimination on 6. Is this fine? Slightly, yeah.
So in the exam, will we have to prove all those steps in between one by one?
See, this one you can reuse, LEM. So this will be called LEM. Okay, this you can, I wanted to come to another, one more thing which you can reuse. This, I think you will have to derive. So wherever I have given a name, you can reuse. So there was one thing
Okay.
that I had given a name to, modus tollens. This, if you want, you can reuse. Okay. But others, you have to derive. See, now you remember. Later, you have to again I mean, it becomes difficult to. But anyway, during the exam, I mean, you are allowed to look at your notes. So you can just derive it, or you can just say that using this from the example in class. At least you can give the name of the lecture, so that I have something to go back and refer to. Okay. So
Okay, sir.
unfortunately, I have not given numbers to these examples, but if you want to reuse something like this kind of a thing, you just say as done in lecture so and so, and in the PDF there will be a slide number. Okay.
Okay, sir.
Yeah.
And if something from the lecture comes, then we'll just write from this.
Yeah. If by mistake I give you something from the lecture, just say that just go and look at your
Refer to this.
lecture number 8, this thing. So it's possible that I don't see what is done in the lecture, but now that you point out, I will try to cross check as much as I can. Okay. So, anyway.
Okay, sir.
Yeah. So is this part clear?
Sir, in the previous example,
This
sir,
one.
was it equivalent to De Morgan?
It is. But we will not apply De Morgan. We want to write a proof like this. So this is the point. We don't want to look at it as using semantics. Okay. I don't want to look at it using the meaning of those statements. I write this. I want to be able to syntactically rewrite things so that I get this proof. That is the point of this exercise. So once again, you are again looking at it as a truth table.
Yes, sir, I was just asking.
Yeah, no. Yeah, correct. This is just the De Morgan thing. But you see that that requires some effort, actually.
Yeah, we proved actually that.
Yes.
Using this proposition
Correct.
and logic.
Yes. Yeah. Okay. We have a rewriting of that. Okay, so let me go to the last example that I have for today, which is this one. This is yet another De Morgan. Okay. So try this out, and then we will stop the lecture after this. So let me actually do this. So there are several ways of doing this problem, but I'll be using this previous thing, this LEM as a rule. I can always use LEM anytime. Okay. And then, so there are also ways to not use LEM and then kind of derive it internally. So first of all, I have not of P and Q as a premise. Okay. I'm going to use LEM, that is P or not P. I can always use LEM with some instantiation of phi. Okay. So now I want to derive not P or not Q. And thanks to this, somehow if I'm able to do not P or not Q from both P as well as not P, then I can use the OR elimination to get this. Okay. So this slightly, oh, why did I write 8? Okay. So now I assume P. Okay. Now inside this, so I want to get not P. So if I get, I want to derive a bottom. Okay. No, sorry. I want to derive not P or not Q from here. Okay. So what do? Is once again, I assume Q within this context. This will give me P and Q by the AND introduction on 3 and 4. Now this gives me bottom due to premise and 5. And hence, what can I conclude? I can conclude not Q. Okay. And then I can use my OR introduction to get not P or not Q. Okay, so this is the negation introduction done on 4 to 6. This is the OR introduction done on 7. Okay, now I need some more space. I will continue. Now I will assume not P. Okay. And just do OR introduction. Okay. So now you see inside this box, starting from P, we have derived not P or not Q. Starting from not P, we have derived not P or not Q. And we have a P or not P. And then I just use OR elimination. Use OR elimination on 2, lines 3 to 8, 9 to 10. And you get not P or not Q. So somehow this making use of the LEM was useful, because then I could assume this, derive this, assume this, derive this, and use OR elimination. So there are ways in which you can avoid using LEM. I'll leave that to you as an exercise. Okay. So the point is, so we have seen several rules. You can also use LEM whenever you want, if you think that is necessary. Unless the question asks you, don't use LEM. Okay. And so these are all the natural deduction rules. Okay. Now let me summarize and then I'll stay back for questions. So this is the end of the logic module. Okay. So essentially we have seen some kind of a calculus for reasoning about propositional statements. And we have seen that it can be used mechanically to solve logic puzzles. Like, so sometimes you are given puzzles, like there are arithmetic questions. So there are so many things of this, like then you say let x be this, let y be this, and then from the question you derive 2x plus 3y equal to 4, 7x plus 8y equal to something, and then you solve for x and y. So that was arithmetic. Here it's propositional. So you know that from the given question you have P, and you have P implies Q, then you can derive Q. That is the analogy. Okay. And sometimes logic puzzles can be seen as sequence. Okay. And the last two lectures, we have seen how to write proofs of sequence using these pattern matching natural deduction rules. So essentially, they are modeling the way you write proofs, except that these rules have picked out some particular arguments that keep coming from time to time, and then you just know. Just by using that, you can derive whatever you would have derived instead of writing the entire thing in English. Okay. It can also be shown that every valid sequent can be proved using rules of natural deduction, but I'm not going to do that here. For this course, as long as you're given a sequent and you're able to apply these rules and write a proof of that sequent, that is enough. So this was an exercise in kind of methodically writing proofs using pattern matching. Okay, so that's it from my side for logic. So I will stay back for questions, but I want to say that we will have one quiz on logic sometime early next week. Okay, so try out the tutorial problems. Maybe you can have a couple of 1 or 2 tutorial sessions just to get acquainted with all these natural deduction rules and logic puzzles, and then maybe early next week we can have a second quiz, and by the time I will try to give you the answer sheet of the first quiz. Okay, and for the course I will teach one more module which will be on automata. So I will need 3 to 4 more lectures. So I will teach on Thursday, and if needed we will have 3 lectures next week. Okay, so that's it from my side.
We won't be doing graph theory.
I don't have time, so I mean, so this course is supposed to end by January. I can take 2 more lectures later in Feb, but it will be extra it's like extra load. If maybe
Okay, fine. So lesser load for us then.
You can take a poll within your class. If many of you are fine with having, kind of, see, February 1 to 4 is not good for me. That week is busy. So if needed, I can teach the week after that, the second week of February. But then it will, so then there's a question of exam. Like it will be there for the exam. Like so you have.
So then everyone will agree to lesser number of topics to be in the exam.
Yeah. So
you can assume that.
Yes. So I think the answer is there. So I think graph theory will be taught, part of graph theory will be taught in some other course, I think some algos or. So that's why I wanted to teach automata and then leave out graph for some other course. Okay. See, I think we have had enough material. I think it also takes some time for the digestion to happen. So there's no point in like overloading with extra things within this. So you just solve more problems in this, and I'll teach automata. I'll also give you some problems in that. And then the second week of February, we will have an NSEM. Okay. So there's 3 modules plus NSEM, 2 quizzes and 1 NSEM, where everything will be there. Okay. Yeah. Okay.
Okay, sir.
Yes.
Now that we have proved the sequence using natural deduction rules, the Boolean puzzles or such kind of things that we have done in the previous classes using just the simple, we have not used natural deduction rules to prove them, right?
Yeah, yeah.
Now can we use the natural deduction rules to solve such puzzles in exam?
Yes, you can do that. It is up to you. So you can either try to give a direct proof, or you can try to write a sequent from it and then just derive the sequent. Either way.
Okay.
Okay.
So one more thing, can we just move to the previous slide?
Yeah.
So here I wanted to ask a more general question, like when we are to prove such sequence where the conclusion includes an or disjunction, is it a good way to show or prove just the first part or just the second part and then use disjunction introduction, or should we prove it like we have done in this example?
No, it depends what is the premise. See, if
No,
I had, okay, like if my premise was this, from not P derive not P or not Q. Okay, so immediately I write not P and then I just write not P or not Q. So it was good to get, or maybe this not P is hidden somewhere, like something like Q implies P, or sorry, P implies Q, or let's say P implies R. P implies R, P implies not R. Okay, then the way this not P or not Q is becoming true is because I can derive not P. See, if P is true, then I am getting R as well as not R, which is a contradiction. So in that case, I get not P and then I get not P or not Q. So there is no general method. You have to look at the context and figure out how to
I'm
get
just saying that somehow if I can show while proceeding, if I can show that if I arrive at not P or if I arrive at some step to not Q, then can I write in the next step that not P or not Q?
Yes, you can. Yeah, there this if in this case not Q could have been replaced with anything else, you could have written that. Yeah. Yes. Yeah.
Excuse me, sir.
Yeah.
Sir, so in this question, we have assumed P and then inside the context of P, we have assumed Q, right?
Yes.
And then we are getting P and Q. And then when we are getting not Q, that is like when we assume Q and we get a bot, so we are getting not Q.
It is inside the context of P.
Yeah. Again, so not Q is also inside the context of P.
Correct. Yes.
Okay. Yeah, got it.
Yeah.
I was confused as in not P or not Q should be outside the context of P, but yeah, got it.
Yeah. So you remember the OR elimination from phi, I have to get chi inside this context.
Yeah.
Yeah. So there is a question about why there is no specific rule for double negation. I mean, you can write it as a rule, or you can even derive it. I mean, it's derivable. So these are somehow some kind of minimal set of rules. If you discard LEM, then the rest of them are derivable. So you can either write a derived rule or so. Yeah.
Sir, can you go to the LEM example?
This one, the proof of LEM.
Yes. So here, before deriving the not phi or not phi, we are already deriving not phi. So can't we conclude phi or not phi from this?
So yeah, this is what I did, and then I retracted. So I have not phi, and then I'm deriving phi or not phi from here. This is what you're saying.
Before it, I mean the second step.
Here.
Yes.
No. So if possible, you can see. Let's say, I have this, and from here I have derived this, not P and not Q. Okay. Okay. From here I'm deriving not phi. I mean, let's write one extra step to say that I'm writing this. Okay.
No, I was saying that before coming to the step 2, aren't we gonna show the steps how we came to the step 2?
Yes. Normally you should do it. Just because I did this here. Yeah, correct.
Yes. So before coming to the step 2, while deriving it, we are already getting a not phi and not phi.
Correct. Okay.
So we can conclude from that.
I see. So you're saying
phi or not phi.
Yes. Right. So you can you get not phi here, and then you get not phi here, And then you'll use the bot introduction on this and this. Yes, yes, you can do that. Yes,
Okay.
I agree.
Okay.
Sir,
Yes.
in the last example where we use alien, if we,
Sorry.
yeah, there is, matlab, sir, we are anyways proving not P or not Q here, assuming P and Q. So why are you using alien?
No, I want to. Okay. No. What's your question?
Sir, like if we assume P and if we assume Q, then we will just come to this conclusion number 8 directly. So
How?
I can't understand that what is the use of alien here.
Okay. How do you get this thing finally? Not P or not Q? Outside the assumption.
Oh.
Right? So you get not P or not Q inside the context of P. You get not P or not Q inside the context of not P. But I want it outside. For that, I'm using LEM because I can do the OR rule, which is phi or psi. From phi, if I derive chi, and from psi, if I derive chi, then I can write chi.
Okay. Fine, sir. Fine. Understood.
So,
Yes?
adding to her question, is there a way to get not P or not Q outside the context of P and Q?
Using this method, no.
Okay.
No. I mean, here I cannot write not P or not Q outside. No. See, because not Q comes within the context of P. See, because I'm using this P and Q here, right? Because this uses this context. If I write it here, then this will be wrong. See, this is true only because I have used P and Q here. And that's why, I mean, it is inside the context of P.
Yeah.
Okay. So there are other ways of doing it without LEM. You can try it out. Okay.
Just before someone asked that in the proof of LEM,
in the proof of LEM,
like you can, and you can in the intermediate step between 1 and 2. So you said that you can conclude from the previous example, but it will come in the box, not outside the box.
No. See, this not P will come outside the box. See, if you assume phi, see if I'm doing this previous example, let me just copy the proof here. Okay, if I just use this previous example, so what do I have? I have not of phi or not phi. Okay, then inside that I will assume phi, which is this, and then I will come to a contradiction, and then I will get not phi.
Yes.
And then inside this again I will have not phi, and I'll come to a contradiction, I'll derive not phi. Okay, so within this box I have derived not phi and not of not phi. The question was, there is no need to add an extra and then do this. So you would have, by that time when you write this itself, you would have gotten not phi and not phi, and then you just introduce bot. So you don't need to.
Sir,
yes.
Sir, in the quiz, will you like explicitly mention whether we are to prove something using truth table or natural deduction?
There's no truth table proof at all. Everything will be, I mean, at least if I give you a sequent, okay, it will be by natural deduction. I will not ask you to enumerate the truth table.
Okay, sir. Thank you so much.
Yeah. Okay. Anything else?
So, in
Yes.
the question where somebody else, where you had the rules for bot, there was a example after that where somebody else told an alternate solution, I think. So,
okay. Which was that? Probably this one, I guess. Yeah. Yes. Okay.
Yeah, this previous solution.
Okay.
Yeah, the next solution, I mean, sorry.
This one?
No, the next one.
Okay. Okay.
In this solution, where in the fourth step we are introducing bot, then later towards the lecture you said that we introduce bot in the context of the assumption.
So the context of the assumption is, the assumption here is P.
Yeah, but then when we are assuming Q.
No. Oh, you mean here?
No, the fifth step.
No, here you are deriving Q.
Oh, sorry, deriving Q. This isn't in the context of the assumption where we assumed P and introduced bot.
Yes. So you can deriving P implies Q. If you assume P, you will be able to derive Q. That's what this means. You understand? See, we are inside the context of not P. Okay. Now inside this not P, I want to derive P implies Q. So this is what I want. And if I want to do that, I will have to open a box and I'll start with P and I have to see if I get Q. This is what is going on here. So I started P. Since I'm in this context, I get bot. I'll write it. So here this is assumption. And this is by using bot introduction on 2 and 3. And this is what is this called bot elimination on 4. And this is the implies introduction from 3 to 5. Is that clear?
Yeah, it is. Thank you.
Okay, so yeah, Megha, you have a question? Yes.
Yes, so in the problem set 3, the 17th question, it's just a statement which goes like, no statement is true.
Yes.
So now this is a variation of the liar's paradox, is it?
The state.
I will not answer this. I will leave this for the tutorial. Okay. So,
no, so just
yeah, it's like saying I am lying.
Exactly. It makes sense in the context of the problem set, I think.
No, I'm not asking about the answer or anything.
Okay. Yeah, it's a paradox. Yeah. So it's like I am lying.
No, but I wanted to ask, is it a logical paradox or is it just a semantic paradox? Because I was talking to someone about this and he told me that it's not a logical paradox. It can't be a logical paradox. At best, it's a semantic paradox. So I started reading more about it. And then I told him that, okay, I'll try to prove it logically. And I tried to assume the statement and use the natural deduction and see if I could come to a paradox. And I couldn't come to a contradiction using just the natural deduction rules or the axioms of logic that we use to derive any conclusion. So I started wondering whether is it actually a logical paradox or is it just a semantic paradox?
No, wait. So what is a logical paradox? So first we need to kind of, be clear about what is a logical paradox.
Yeah.
Okay. By semantic paradox, you mean like it doesn't make sense. This is what you mean, right?
Right.
Okay. So yes, indeed, it doesn't make sense. So it is a semantic paradox.
Yes, definitely.
Now, but then if we want to say it's a logical paradox, then we need to know what is a logical paradox.
Mm-hmm.
I don't know. We need to, you need to tell me what is a logical paradox.
Okay. So even I didn't, I didn't consider that I should read about it. I just thought that if it is something that reaches a contradiction while using the rules of logic in its proof, then it is a logical paradox. I mean, common sense tells me that, but I haven't read about it.
No, I think in some sense you are using the same, your logical paradox and semantic paradox are meaning the same in the way you're
Yeah, I think
okay.
so.
So
No,
yeah.
I just wanted to know if there is a proof which conclusively tells us that it is indeed axiomatically a paradox, this the liar's paradox. Because in some places, I didn't go through all of it because I don't know enough mathematical logic to understand all of it, but some places they said that it said that the liar's paradox, the proof of it has a few fallacies. The fallacies I didn't understand, so I was hoping if you could tell me a little bit
So
about.
wait. So I need to know this. See, it's a question of what you want to derive. See, it will be something like the LEM, or it's something like P and not P cannot be true. So not of P and not P should be derivable, right? So I mean, I don't know how. So you should try to write a proof of this. Try to derive a. Where is this? Without any premise.
Yeah.
One should be able to derive. It's not the case phi and not phi.
Okay.
Okay, this should be derivable. Like, I mean, I can apply LEM to get phi or not phi. Okay. And then possibly using the same thing. I mean, okay. We use this thing, no? P, what was this? Not of P and Q derives not P or not Q. Okay, wait. Essentially, I want to say that, yeah, of course. Wait. This is simple, no? See, if I have phi and not phi, let me assume this. Okay, I have phi by the AND elimination. I have not phi by again AND elimination. I get a bot.
Yes.
Which means not of phi and not phi is derivable.
Yeah.
So, I mean, which means that you will never be able to derive phi and not phi.
Correct.
See, you can derive only phi or its negation. You will never be able to derive both. Then there is something wrong with the proof system.
Exactly.
This is as much as we can say.
Okay.
But that problem is much more, I think that's different than just proving this. Because it looks at the set of all statements and then it looks at this. So I'm not sure you can, it just doesn't make semantic sense.
Right.
Okay, I don't think you can, see, first of all, it's not like a sequent. Prove something. So first you have to try to write it as a sequent, if at all.
Right. I was actually trying to do that. I was trying to write this statement mathematically and then go about proving, but I couldn't reach anywhere.
So not using natural deduction rules. You can just get a contradiction just by.
Yeah, by using arguments that if you assume this statement to be true, you get a contradiction. If you assume it to be a false, you get a contradiction, and that's why paradox.
Yes.
Okay. Okay.
So it's not immediately clear to me how to write it as a sequent.
Yes, exactly. That is where I got stuck. So I thought I'll ask. Yeah. Thank you, sir.
So somehow, like, you have to derive bot from it.
Okay.
Yeah, it doesn't fit into the sequent thing. Actually, I don't think it fits immediately into the. I don't see it immediately. So, okay.
Sir, the problem said 3 has a hidden message. Did you see that?
I am not responsible for that. Okay.
No, we know who's responsible for it, but we just wanted to know if you.
It was indicated. So yeah.
Okay, sir.
So
thank you.
Did you try out the problems? Are they? Yeah.
Yeah, I reached about halfway, and so far they are doable.
Okay, good.
Yes, so we solved the we are solving the problems, but we are facing some difficulties while writing it. So I think I will ask TAs about it.
Yes. I think so. This is the entire point of this module, to be able to write proper logical proofs as much as possible. Okay. So Yeah, hope this will be a good exercise.
Yes, sir.
Okay. Yeah. Any other questions? Okay. If there are no other questions, then maybe I will stop sharing. I will get rid of this thing because this will only confuse why this is here. Okay. So.
Thank you, sir.
Yes. Okay. Thank you, everyone. Yeah, I will stop sharing and I'll end the lecture.